I'm going to bring the discussion to the higher energy regime to talk about collective phenomena in small systems. So I'll put a special emphasis on small systems. So I will tell you what I mean by small, how small it is. Actually, it's smaller than most of systems we have been discussing in this program so far. And it's also something I have been mainly working on over the past many years. So I'll tell you where within the collective effects, how we have found it, and also I want to discuss some recent new ideas that we are still developing, working on data analysis. In what other small systems we maybe will see some very interesting collective effects. To start. Yeah, so this is a standard paradigm of High-value calculations that we have seen this several times in this program. And so basically, that the connection that between the low energy part of the nuclear physics and the high energy part of nuclear physics is that starting from the initial condition, we have some the nucleus has certain shapes, and the initial collision has certain shapes, and under the evolution of the quark-gluon plasma, which can be described by the hydrodynamic evolution. We in the final state, we measure this azimuthal energy. The collective flow effect, right, can be the azimuthal and isotropy flow. So we see that from the phi distribution, and also so-called radial flow effect, which we measure from the transverse momentum spectrum with kind of radial push to the overall particle momentum. So one thing that, although this is a picture that people are very familiar with now. We should ask the question that, so the link between the initial state and the final state, and how good it is actually, and actually why it works. But I'm not sure, especially to the low energy nuclear physics community, whether this is obvious to me that the system like this should behave hydrodynamically, right? We are talking about a system that has a size on the order of 10 Fermi, and it produces particles in the final state, a few hundred particles, a few thousand particles. Whether it's obvious that it should behave hydrodynamically. And certainly, like the water, so that be more many other magnitude more particles, right, to develop kind of collective effect. So indeed, if you read the 2015 long-range plan document, and what it says is that so the emergent phenomena that the volume of quarks and gluons at extreme temperature will form a nearly perfect liquid that can be described by the hydrodynamic came as a complete surprise, and this leads to intriguing puzzle. So in fact, in the early days, this is something that actually most people have not expected. So now we all have accepted based on the experimental observation. This was a surprise. Now in hindsight, the question is this still a puzzle, right? And or maybe this is naturally expected, somehow related to the fundamental nature of the QCD. This is still an open question, and here this describe how what's the other future program that will address this in the future. So I think you've seen this from John Eve's talk if you are here in the first week, and this is still my favorite way to see this collective flow effect in the High-value collisions, the light collisions, which we call the large system, where you look at two particle angular correlations in the delta eta and delta phi. And what you will see that along the delta phi axis, you clearly see this cosine 2 phi distribution. And this structure extends in our entire rapidity coverage, so indicating that this is some kind of global effect. It involves all the particles. They produce in this elliptic shape in the aligned over the entire rapidity range. And now, if this is what we established in the large system, so what happens if you try to go to a small system? Can we actually turn this effect off? Well, actually, you can. Let's say we go to the small system. In the extreme case, in the proton-proton collisions, right? The size of the system factor of order of magnitude smaller. You can see the correlations that the structure of the two-part correlation are drastically different. And the biggest difference is this structure at small delta phi, the enhancement small delta phi over large delta eta. This is missing from the proton-proton collisions. This is what we call the ridge, or near side ridge that kind of considers the smoking gun signature of the flow effect of quantum clusters. And you see, and here you can say this is kind of expected, right? If you have a large system the size of 10 Fermi, your mean free path is small, sufficiently small. Let's say on the order of Fermi, you can. So this is sufficient to develop the hydrodynamic behavior. You have very strong interactions. Whereas now, if you reduce your system size to the extent that it becomes comparable to your mean free path, then the system should become dilute and all the effects should go away. Right? So this seems to be consistent with what we expect. However, the surprise came in 2010. So this is right after the LHC has started, and we see the ridge or the flow effect also in proton-proton collisions in an unexpected way that no one really had expected that. So here, so we're looking at proton-proton collisions, same the two-particle correlations, where it is small, but you can see there's a tiny little enhancement here. There's a small ridge here that we see not in the normal proton-proton collisions, but in events where in a single collisions you produce a couple of hundred particles. So those are rare events, but they can happen once you have a very high intensity collider. You can produce those events still in an abundant way. So those events, they are the initial size is still small, but you are looking at some final state but much denser compared to the regular PP collisions. So in those type of events, we see some hint of that may indicate there's some formation of the QGP droplet, the perfect fluid, with the size of like the Fermi scale. And of course, that because that was unexpected, can also turn the argument around that if we've seen this in a place that we don't expect it, maybe this is not a signature for QGP. We don't have QGP anywhere, even in the large system. So later on, so that's the beginning of the small system surprise, and later on the LHC had the proton-led collisions. In proton-led, the system size might be a little bigger than proton-proton, but if you consider the overlap region between proton and the lead is still substantially smaller than lead collisions. But there you can see that we see a substantial this what we call near side region cosine 2 pi structure, right? And basically, if you put three systems side by side from small to large system, we see a similar behavior. And at first look, and this seems to be surprising, not feasible experiment when you think about proton-proton collisions. And that the reason we're colliding heavy ions instead of proton-proton is to create a large system, so that we can see this microscopic behavior. But it turns out we can actually see all those all the way down to small system. But now, if you think about the fact that you can also make a small system much denser. In those systems, you can also have the multi-particle interactions, and they can rescatter from each other. So you can apply this picture in any system, regardless of the size. Right? In this picture, there's no absolute scale. There's no absolute scale here. You can call this is 10 Fermi, 1 Fermi, right? And so in a proton-proton collisions, so you could try to increase the lifetime of system by increasing density. It has been a lot of development over the past years, and this slide is kind of a condensed summary of the many years of development. That a lot more measurement has been done subsequently. For example, we measured the V2 for different species of particles, charged hadron, the K0 short, and lambda. And if you compare all three systems side by side, they follow kind of certain ordering. So the heavier particles, they tend to push to higher PT. So the mass ordering effect, which you will expect from this final state interaction effect. Yes.
So in the PP equations, are there some events where you see no elliptic flow, they're just smack on head?
Yeah, so we see this, this is average over many events. So we wouldn't be able to tell event by event whether you have flow or not.
100 particles.
Yeah.
Maybe to follow up, I mean, even in lead collisions, you always get these BN distributions, and you can see that some of them they're not necessarily exactly related. You just don't think it, so.
Yes, relatively small effect.
I didn't quite understand why the lead and the P-lead look so different. I mean, they're exactly the same cuts, right?
These look so different.
Well, the Y scale is different. It's, and then also the how do you call it? The peak also.
Oh, the peak. Oh, okay. That's right. So the total number of tracks is the same. Now in P-lead, you tend to, when you cut this number of particles, you tend to have a stronger bias to higher momentum particles because of the presence of the jets.
Only one probe.
Yes, you cut on the tail of the multiplicity distribution. So you tend to have a stronger bias to the harder process, which tends to produce more particles.
And the normalization.
This is the correct normalization. And what happens is that in P-lead, you tend to bias to a harder process that enhances this peak. The normalization is the same. The normalization is related to the PT spectrum. Yeah, so in this case, you tend to bias to a harder PT spectrum. And I didn't mention this is for particle for PT 1 to 3G. So within this range, in P-lead, so this is the total number of particles. So we count total number of particles, and this the spectrum is harder in P-lead than in lead. So that's what it means.
The mean PT is also higher.
The mean PT is higher. It is highest in PP actually. The highest PP. But when you cut the same number of particles. So this is identified particle V2, and then the V2 also measured using the multi-particle correlations. You directly measure the V2 by correlating multi-particles 4 and 6, 8, and what you will see that the V2 you get, the magnitude of V2 you get is independent of how many particles you correlate together to extract it. So this is directly shows you that this is a collective effect. So this V2 involves all the particles in the events. So basically, you've seen this universal QCD collectivity across all the system, and there are a lot more measurements. But I think it's pretty clear that the role of this strong final state platonic rescattering all the way down to the sub-Fermi scale is clearly seen. And now, do you call it hydro or not? So I put in parentheses. I think this is still debatable. Whether they are in a regime, whether scattering enters a regime that can be effectively described by the hydrodynamics with sufficiently low viscosity, this is still being debated. In those small systems, actually there's other theory without using hydro that can also describe a lot of the observables. So yes.
Can you explain to me, for example, you have a set of points which are reddish brown,
yeah,
and they're higher than the other points. What's the difference between
yeah,
those?
so that's right. That's good question. So this one is measured using the two particle correlations. And whereas all these points, they are measured by correlating 4 or 6 or 8 or more particles. So the difference here is related to the fact that the V2 is fluctuating event by event. There's an event by event fluctuation, which leads to a difference between the value you extracted from two-particle correlation versus multi-particle correlations. Yes.
So the red points are selected events where you only have two energetic particles?
No, these are the same events, but you can calculate V2 by correlating two particles at a time. So you make all the two particle pairs.
I see, okay.
So these V2 means you sample 4 particles at a time, and you make all the 4 particle combinations. You
Oh, I see.
calculate V2 to the 4th power. Then you calculate V2 to the 6th power. So if everything factorized, so if this is effect involve all the particles, and at the end of the day, you should extract the similar V2 value.
Yeah, it's sort of a quirk about exactly how you define them. Like if we're Gauss, if the fluctuations are Gaussian, then all the higher ones should be equal and the two particle one should be higher. But
Yeah.
it's just sort of exactly how you define it.
Yeah, there's a subtlety here. I cannot avoid it to go into detail, but basically, yeah, if you, without looking at this, and what it says is that this is a correlation that involves basically all the particles in the events. It is not some kind of short range correlations, which will diminish as you correlate more and more particles together at one time.
So what Matt says, of course, very true, and I think it's also useful. So if you really factorize it and you're in this high multiplicity regime, then this V22 is, you can prove that it's the real ellipticity plus the standard deviation over 2.
Mhm.
And V24 is the real ellipticity minus the standard deviation over 2. So it's really kind of well understood, like what's the difference between these two, and it's exactly the number of fluctuations in this V2
Yes.
distribution.
Yes, that's right. Yeah, that's right. So the difference between the two tells you about the V2 fluctuation, even by event.
I'm just curious, so for the PP results, those are old published results. Do you also have the new results based on the entire long two data?
Yeah, these, no, we don't. Just one thing to mention, that to get the data to do this, we have to take special runs from the LHC.
That's how much the trigger data.
Yeah, so we need special run condition where they have to bring down the luminosity. Otherwise, the so-called pile-up effect is. So in one bunch crossing, you can have like 50 interactions happen at the same time. So you cannot tell whether your high multiplicity events come from one collision or from just the pile up of multiple collisions, which will be boring. So we have some better data, but not a lot more. So,
I'm just struck by the error bars.
Mhm.
So I would expect the V28 or V26 will have much bigger error bar than the V24.
They do. I think maybe.
Doesn't increase that quickly.
Maybe you just.
It's almost the same.
Because they are, yeah, if you zoom in, they do have bigger, but they are just very small on these scales. But you're right, the higher order generally have a lot of uncertainty. Hard to see from this. Okay, and also to show you one study of this is the PLAD V2 as a function of PT comparing to the various theory. And one thing that we learned from all these small system studies is that to be able to describe this flow in small system, now we start to be sensitive to the initial geometry defined by the shape of the proton. So that's something you don't have to vary too much in the large system. You just assume they are spherical, right? However, that if you want to, if proton collisions have V2, V3, and all harmonics, we have to get the shape of the proton correct. That's as shown here in this model, the IP Glassman calculation. If you assume a spherical proton shape, you don't get enough V2 to describe data. Whereas you have to assume this kind of proton shape with 3 hotspots that you can get close. But of course, there are also models that, the other degree of freedom you can play with. You can change the E or S, or this model has pre-flow, some kind of before this hydrodynamization, you could also describe data. But this is kind of a challenge that the initial state is harder to control because, to model the shape of the proton, that's difficult. But on the other hand, it's also an exciting opportunity that we have some data that are sensitive to the shape of the proton. That yes.
So do you expect to see flow for electron proton collisions?
So electron proton naively you wouldn't. Because
Yeah, what is the difference between proton proton versus electron proton?
the proton you can still kind of think there's a geometry because proton has to still have a physical size, right? And you can, if you think there are three hotspots in the proton, so they give you some eccentricity. There's some initial eccentricity of proton-proton collision. Whereas if one particle is a point, exactly a point, then you don't have a geometry, you don't have eccentricity.
But I'm just thinking, but the point could strike one piece of the proton or the other, and you could have an elliptic flow, I would imagine.
Yeah, it doesn't seem as obvious to me, like, all of these things come from fluctuations.
Yeah.
In the interaction, so why couldn't there be fluctuations in that interaction that would?
Yeah. So actually, I'll come to that.
Okay.
It's,
You won't use that high multiplicity.
Yeah.
it's a good point, actually. But yes, go ahead.
Are you certain it's 3 rather than 2 and not 4?
Right, that's we don't you have a lot of degree of freedom to play.
3 is very convenient to say maybe it's quarks.
That's right. That's right. You can fluctuate different ways. Basically, you need some fluctuations. I think the message here is spherical is probably not enough, and you need some shape fluctuations.
So they've done Bayesian analysis of this, and I think there's been a few different ones, but kind of the general consensus is you can get a minimum, but after that, it's completely constrained. So
What's the minimum?
yeah, it's like 3, right? So-
Yeah, more than one. You need more than one.
Yes.
I wonder what the electron scattering experiment would say about the shape of the proton or polarizabilities.
So the electron scatter, the thing is, we're seeing these are fluctuation, develop like fluctuation shapes, where you don't have that information from the electron scatter. So on average, they still spherical. I mean, the proton on average is spherical.
So this calculation is already constrained by EP diffractive. So that three hotspot not a top is already constrained by the J-side diffractions.
The dash.
Then you use that as an input for NDI as some consistency.
And also there has been measurements of flow in E plus, E minus, was it E plus E minus that Andy was looking at, where there was no flow, it was like exactly zero.
I'll come to that point.
Okay, sorry to ruin your punchline.
But yeah, we'll go to a smaller system. This is not small enough yet, actually. I'm going to go even smaller. This is a little more technical plot, but I want to mention, since in the last week we talked about this VNPT correlation, right? How you constrain the nuclear deformation. So we also measure this in small systems from the BP, PLED, and LED, where you see that so in LED, this is also measured by Atlas to much higher multiplicity. This is in the relatively low multiplicity range, peripheral events where at some point, it's changed sign because of what drives the V2 from the geometry dominant region to the fluctuation dominant region, and then it goes up, tends to goes up, and to others haven't seen it go back to positive, and we see some sign that go back to positive, and it was argued that this is something you can use to distinguish whether at the low multiplicity you see the source of correlation from other than from the geometry, but some initial momentum and enthalpy. In PLED, we see that it depends on the acceptance we take. We see sometimes goes to positive, but in proton we also see it goes to positive. But if you look at what you get from the PCR, the PCR has no flow effect, right? We see that in proton, the PCR can qualitatively describe the data, which indicates that the non-flow, so the non-flow effect is actually still very important, very significant in the low multiplicity region for this observer. It still needs to be well understood in order to really extract information about initial stage, for example, from these correlators.
So why you say low multiplicity? From the picture, I would say high multiplicity. But the deviation larger and larger from zero.
No, I think I'm referring to this change sign to low multiplicity to positive, and it was argued that it will be an indication of the initial momentum correlation as implemented in the IP Glassman model.
But they also claim the IP Glassman with the CGC with the short range correlation 0.2, 0.4, and here you apply the eta gap larger than 1, maybe even larger, which means you don't have CGC effect in principle.
No, CGC is a long range effect. So
That's what the
I think we all have some other words. We also find that the correlation may not be very high.
okay.
Can I ask you a question about the units and the y-axis? What is that exactly?
Yeah, so this is like a Pearson coefficient. It's kind of normalized. So its dimension is a correlator. Tells you how strongly the V2 and the MPT are correlated with each other.
Actually, between -1 and 1.
Pearson correlation.
Yeah, it goes from 1 to -. Okay, so now let me, so it's evident that this QCD collectivity or signature of the QGP liquid, they're not limited to the large system, right, AA collisions. So the question is how small is too small that we stop seeing the effect. So far, we see the effect all the way to the PP collisions. So under what condition, right, this platonic collectivity would emerge? And going back to the question I posed earlier, so is the platonic collectivity we observe in this extreme small scale, are they really unexpected? Or is a natural consequence of QCD in its non-perturbative regime? What I mean is that when we look at the QED system, right? The QED multi-body system. So QED is intrinsically a weak force in two body. Therefore, if we see a strongly correlated QED system, that is surprising, right? There's an emergent effect that from a weakly coupled series become a strongly coupled system. However, the QCD force is intrinsically strong, right? Not at very high temperature. So in this sense, the emergence of the strongly correlated QCD system is probably less surprising than the strongly correlated QED system. Maybe it's built in somehow. No matter how small system we go, it's always there. It's just a matter of how we observe them. In some limit, it's harder to observe. A very high, small, low multiplicity system, maybe they're still there, but we just don't know how to observe them. So there's an attempt to look at even smaller system. E plus, E minus, this is two-part correlation in E plus, minus. We don't see a ridge in the electron-proton collisions. This is observed. You don't see any ridge. And people also look at ultra-peripheral collisions from the gamma A collision or gamma P collision. So on there, you can imagine you have some photon turn into a dipole. So you can, let's say, look like a pion hitting on a nucleus, right? And there's a little subtlety here. I'm happy to discuss it. Interesting. So you can always extract the V2. You can always extract the V2. You don't see the near side ridge, but you can extract the V2. But then how you interpret the V2? But there's so-called non-flow effect. You have to subtract the non-flow effect. How you actually subtract it? So the V2 has been extracted, but the interpretation of this V2 is still unclear, has still being debated. But I would say it's inconclusive. For these systems, it's inconclusive. Whether we see the flow effect or not, but it's intriguing. And all these systems are limited by the multiplicity. So I don't think we can say that E plus E minus has no flow effect yet. But the multiplicity has been probed is really limited. This is how many tracks? I don't think. So like for example here, 15 to 30 tracks compared to the hundreds of tracks when we look at this is high multiplicity is very important for us to see the the contribution from the collective effect to overcome the contribution from the non-collective effect. So So basically pushing to higher multiplicity is very important. So for all these small systems, if you want to have a conclusive answer, so we have to try to push them to at least a couple hundred particle regime. But right now, it's very difficult. It's very difficult. Now, I want to mention there's an earlier puzzle in E plus minus collisions. In very early days, that people found that if you look at the just particle production, hadron production in E plus minus, so they can describe by a thermal model, the thermodynamic model. So it appears like the particle emission in E plus minus collisions come from some kind of thermal source with a common temperature. That's not expected, right? Because it's commonly believed that these elementary collisions, such as E plus minus, they do not allow this description of multi-particle scatterings. I would say it's not proven, but this is a common belief. So this thermal behavior, there's a suggestion that maybe this is related to the quantum entanglement, that the entanglement entropy will drive the quantum thermalization. So from these papers, to briefly mention, basically the idea is that if you think about the QCD string, the entire QCD string is entangled. The different regions on the QCD string is entangled. There's A, region B, they're entangled. And so if you look at a local region A, it is in a mixed state. You can compute this density matrix. And then you can compute the entanglement entropy for region A. So after you introduce add a fragmentation, you cannot introduce a quench to the system. Then this entanglement entropy would drive the system to behave as appears to be thermal. But there's no this rich or long-range correlation because there's no real final state rescattering. It's a quantum effect. Actually, this is actually a well-known effect in the atomic system. It has been demonstrated. This quantum thermalization through entanglement is without involving the classical interactions, has been demonstrated in the cold atom system. So maybe this is something related to what we see in E plus minus. So that you have two possibilities to explain the E plus minus puzzle. Either there's some kind of multiple scattering effect that we have a QGP-like system, or it's related to entanglement. So both, either way, it will be very interesting.
What does it mean of classical interruption?
The rescattering. So these would rescatter, like develop a flow effect, drive the system to a.
And in this science paper, I mean, the system is interacting.
Which paper?
The science paper.
I don't think so. There's no classical interaction.
Three particles.
Yeah. But anyway, I will. I'm not expert on this paper, of course. But
Is this related to the eigenstate thermalization hypothesis?
yeah, the entanglement serves as kind of a long-range force to arrange the system in a thermal way.
You get thermal averages without any real interaction.
With real scattering, yeah. That's the idea. So motivated by those, with my student and postdoc, we developed. So basically, what we are thinking is that. So what would be the ultimate small system you can have? The QCD system, right? We go from the AA to PA, proton, E plus minus, and electron proton. The smallest system you can have. How about one single particle, right? So you can't make a small system that's smaller than one single particle. So the question I want to ask is whether this QGP-like behavior is intrinsic to the kind of non-perturbative nature of the QCD dynamics. So in general, in that sense that you may be able to see a similar QGP-like signature just from the one single particle as they evolve in the vacuum. So let me elaborate what I mean here. So basically, if you think about the QED vacuum, right? QED vacuum, we have condensates of plus and minus charge pairs that filled with the virtual electric charges. Now, if you put a free electric charge in the vacuum, so what's going to happen? It's going to impact how these virtual charges distribute, but the force is not strong enough to pull them out. So you create a polarization and screening effect. The free charges will pop up when your field is extremely strong, right? From the Schringer effect, when the electric becomes extremely strong, you start to pull these pairs out of the vacuum. But we are really far from that limit. So now let's go to the QCD vacuum. The QCD vacuum are filled with virtual color charges. These are usually called parallel condensates. It can be quark condensates, can be gluon condensates. Now imagine if we put a free quark in the QCD vacuum. This is of course practically not possible because this will be infinitely energy states. But for the sake of argument, if you stay with me, so if we do that, the color force is so strong that immediately it's going to pull all the quarks and gluons out of the vacuum. So this system will kind of the quark will quickly gain kind of mass and through interactions, and this system can expand like a quark plasma. Hypothetical. How to realize such a system experimentally? So this is in the rest. Let's say this is a rest frame. Now if I boost it in a go to a highly boosted frame, so this pattern is moving very fast through the vacuum. So it's like a puncture hole through the vacuum. So it would excite a lot of quarks and gluons along its passage, and this could rescatter and then expand around this axis. So experimentally, to realize this experimentally, what you can have, we know that in proton-proton collisions or E plus and minus collisions, you produce a back-to-back quark and antiquark. But at a very high energy limit, they are quickly stretched out, form a QCD string. Yes.
It's a bit of a funny picture to choose something for the vacuum and treat it as a liquid, right? But if you cannot, well, single quarks are possible, but you can have a quark antiquark pair, and that it would actually build out, right? And that would probably form like maybe a very high PT meson or something like that, like a pion. But in principle, it doesn't matter how much energy it has. I mean, you can always go down to the rest frame and it could be stable particles. So it's not obvious that this vacuum.
It can be stable particle, but it can also break up into many particles.
But after those are then stable, then the vacuum. The problem with the vacuum is that it has a symmetry, a boost symmetry, right? So it's really inherently different from like a particle and plasma, where it really matters how high energy this pion or quark has. So here you could go to some rest frame and then this quark doesn't have much energy and not much will happen. You go to rest frame of the quark, the energy is still very high. Right? If it's nearly isolated quark, the potential energy is very high. It depends on how you create the quark, but
I'm
a little bit hesitant to say that you're really shooting it through the vacuum.
The longer yeah. So let's say in proton-proton collision, I produce digit. Right. Effectively, I knock a proton into the vacuum. At a very high momentum, let's say. Right. That's what I mean.
So particles have some virtuality, of course. So if you start with very high virtuality, it will particle shower into many particles.
Yeah. So basically, for those type of events, So yeah, the question is how those. Yeah, I think there was discussion I had how the virtuality is developed. Whether the virtuality is developed through the interaction with the vacuum.
That's one way to put it. I mean, that's fair. Yeah, effects.
Right,
Well, it's
so-
very high energy, the coupling is weak, so I know these partial showers are fairly well understood, right? So that's.
I'm not sure what you mean by fairly understood. There's no first principle can calculate partial shower, but it's all phenomenological simulation.
There's a pound skills project and they kind of systematically do analog partial showers.
To some certain extent, I think of the soft radiation, they are intrinsically non-perturbative. I don't see how you can use
So far.
all the soft production, which will be dominated by the system I'm talking about. Right. But anyway, so this is a system considering. Now, in the language I'm using is probably a little strange. Yeah. So but effectively, you are shooting a particle into a vacuum. So you can consider a vacuum as a target, right? And so whether we can see any signature of the QGP like flow effect, let's say, if there's exponential development. Maybe or maybe not. So you can find this is a PCS simulation. You can find jets that produce charged particles as many as 100. So within the cone that you define, you can capture those jets. And also one important thing. So here we redefine our axis, right? So we use the jet axis as eta to infinity, and transverse to jet axis is eta equals 0. If you look at the DND eta, sorry, this is the total multiplicity distribution for within a jet cone. So we are cutting this very tail of this multiplicity distribution. We're looking for the very rare jets, where in one particle shower you have a couple of hundred particles produced. But the similar idea to how we find the flow effect in PP collisions. When we're not looking at the regular jets. These are the extremely rare jets. They happen with a probability you have 1 in 100,000 maybe. But we have plenty of them at the LHC, thanks to the high energy. So if you look at the rapidity density of the particle, charged particle, so in this new axis, you will see that in this high multiplicity jets, in these blue points, the peak value of this DND eta star, you can reach 60, 70. And this is comparable to what you get in the central lead carpal collisions, peripheral lead, central P-lead. So in terms of the particle density per unit rapidity in that frame, it fulfills the requirement to see the collective effects as we've seen in this system. So this is the kind of show the kinematic distribution. This is the transverse momentum of the particle with respect to jet axis. We call it JT, and it has this falling distribution for different energy of the jet, different multiplicity of jets. And the high multiplicity jets tend to have a harder JT spectrum. This is distribution, the two-dimensional distribution for the JT and this eta star, the rapidity new frame. And this is kind of similar to the so-called long plane. If you work on the jet substructure, that the long plane is defined slightly differently. So they're taking a log, but the similar information, the two-dimensional distribution in the phase space of the constituent of the jets. Whereas in all of these jet substructure studies, if you're familiar with this subject, so what they tend to do is you try to trim away those non-perturbative components and look at the rest that can be described by the perturbative approach. And as Wilco has mentioned. However, those non-perturbative components that you tend to be trimmed away in these studies, they are of primary interest for us. So those might be the parts that contains interesting facts. So we should always drop them. Okay, So if we do a two-particle correlation in this new frame, okay, let's take PCF for example. This is low multiplicity JS, and this is high multiplicity JS. And you can see to the first order, the structure of the correlation is very similar to the lab frame. Right? You see the near side peak or away side broad structure, but this is in completely different frame. And of course, I expected there's no ridge in PCF. This is PP data in the lab frame. Right? The structure is very similar. Now, this is the high multiplicity PP in the lab frame. Now, if I add, this is fake. If I add 20% of V2, we will easily see this. We should be able to see this in the data. If you do the analysis in the data, we should be able to see.
The slide before you didn't see no inside bridge.
Yeah, so this is PCF.
How come?
Wait, what? So
Would have expected no inside bridge.
I think it's still maybe it's from the scale. I think this shape is, but in general, it's still away side is still there.
Here, the hard part is always at 8 = 0. Is that, am I understanding the frame correctly?
Yeah, no, infinity. So
Infinity.
infinity. Yeah, the hardest part is in infinity.
But I mean, delta eta is with respect to what?
The delta eta is between the two particles in the jet form.
Okay.
Yeah. Yeah, it's not as evident as this, but it's still.
Yeah, no, this is much more evident.
This probably has something to do with the shape of the D and D eta star, because it tends to get narrow as we go to higher multiplicity jets. So not exactly the same as the lab frame. The shape gets narrow. It probably has something to do with.
But normally you also think about this near side ridge is like much longer because you don't have momentum conservation in the eta direction. Like
Yeah.
you take two particles and they can have different longitudinal momenta.
So this triangle shape is more evident in the high multiplicity jets, which is not the case in the low multiplicity. In low multiplicity is flatter, so it's easier to see this away side peak. It also has something to do with scale, and this is we cut it. We cut out the peak. We go much closer to the away side. You can see it's there, right? This you chop more aggressively, and if we add some V2, we can see we should be able to see the ridge if it's there. The 20% is, I wouldn't say it's too unrealistic. It could be. So one can measure the V2 versus multiplicity. So you go from the low multiplicity, so very large, say what I call non-flow. The non-flow will generally goes down as you go to high multiplicity. This is again the PCF, this is V2. So if we have a V2 signal of adding some fake V2, 15%, 10% at high multiplicity, we should be able to see that. If we can measure to the very tail of the jet multiplicity. When you suppress the non-flow V2 significantly, and maybe the flow signal may turn.
D and delta.
Yeah, this is the two particle V2. This is before taking the square root. For delta eta larger than you also take the rapidity gap of 2 units. We only look at the large rapidity part.
It's a very large V1.
Large V1 for momentum conservation, as same as in lab frame analysis. Everything is actually very similar in terms of non-flow. You see, and the question is, do we see some effect at very high voltages?
In this frame, where is the V2 supposed to come from exactly?
It comes from the fact that when you go through, Roka doesn't like my language, but when the pattern goes through the medium and the vacuum, it will knock out the chiral condensates. So it will knock out the free quark and gluons. They will rescatter and expand around the jet axis, the pattern axis. So it's like an expansion. It's like an expansion around this axis.
But it's some fluctuation that produces some angular symmetry.
Yeah, you need some initial fluctuation. So you need some shape of this initial pattern, which is not hard to get. You always get some fluctuation. Naturally, you have some fluctuation.
So it's all from fluctuation. So V2 shouldn't necessarily be the dominant
Yeah.
harmonic necessarily.
But if you consider the viscosity, maybe the higher order will not survive. The V2 is still dominant. Maybe a question to try to motivate interest from the series. So how can we model this system? Such a system, maybe as a hydrodynamic system. You can think about the QGP that highly boosted, right? Maybe that can describe the dynamic of jet fermentation, right? We have never tried that, but who knows? It doesn't work. So you have to start with some initial condition. Of course, the question is how do we model that? One can imagine that maybe some very early splitting. You have into one branch that if the multiple scattering start from there, you can start with some elliptical shape. And this part use hydrodynamics and then hydrogenation. Maybe this can already capture a lot of the property of the pattern fermentation. This is, of course, we should try and see if it works. There are other signatures of QGP. So we have spent a lot of time to just talk about V2, right? Like we flow. There are actually many other signatures of QGP we should also look at. Did they provide important supporting evidence for the whole picture? So one of them is called the so-called strangeness enhancement. What was observed in heavy ion and also later in PP and PLS most system is that when you look at the fraction of the hadrons containing the strange quarks, there is a gradual enhancement when you go from smaller system, low multiplicity, to larger system, high multiplicity. The interpretation is that you create some kind of deconfined medium with a lot of gluons, and the gluon interactions tends to make it easier to generate SS bar. So that is strange enhancement. We look at this in PCA. In PCA, there's no medium effect, right? And we see that there's no strangeness enhancement for jets produced in PCA from just this conventional fragmentation model for long string model. So the question is, if we do this in the data, right, whether we can see some string enhancement in a jet as a function of jet multiplicity. Right? If we do see some, that can also be a small thing.
Maybe it seems to go down as you get a bit there.
There's initially there's some go down and then level off. There's levels. I'm not sure why it's going down. Yeah.
You mentioned talking about the proton.
No, this is a jet. The right hand side is inside the jet.
Yeah, but I'm saying if I look the left panel, there seems to be a suppression of the proton yield, right?
Oh, you are talking about here, yeah. So that's right. Yeah, proton is, yeah. I'm not sure why.
It's quite significant. If I look this, it's like 20–30%.
Yeah, that's right.
Have you run anything for PCL8 plus Rogan and Shelby?
But I don't think they modify the fragmentation. So I don't believe this effect is there, but we can try. And there are many other things you can ask about. Is there jet quenching? Like, is there jet quenching? But in our picture, actually, the pattern fragmentation in the vacuum is the energy loss process. Apologize, the language I'm using. So in our picture, the proton is losing energy in the vacuum. It's interacting with the vacuum medium. So in that sense, it has no fundamental difference from the pattern energy loss in the quark-gluon plasma. The only difference is you are interacting with deconfined medium versus confined medium. The same analysis we can perform in a jet frame for the jets produced in the heavy ion collisions. We can rotate the system. We take the jet axis as the z-axis at infinity, and then the correlation we see should be influenced by the surrounding medium. But in some sense, the two pictures have no fundamental difference.
Well, this one.
So in this system, you have a little more color around.
Makes some sense.
Okay, so now if we don't see any of these QGP signature in this kind of PCGS, and again, come back to the original puzzle, why we are seeing these thermal effects in plus and minus, right? So maybe this is this will be indicative of the entanglement effect. Maybe that's the reason that's drives those thermal effects. Anyway, so yeah, we're working on the data analysis. So stay tuned for the first results. So these studies are being done at LHC, and in the future, if we have the future circle collider, so we have a lot more risks. That will be even better. And so these are the QCD machines. These are truly QCD machines that will produce ample high multiplicity PCGS that we can perform this analysis. Yeah, so I will advertise that you can see the first experimental results and go to the initial stage conference organized by you.
Try to indicate that we should accept your abstract.
Absolutely. So since we are looking at individual,
24,000, that's for the high luminosity, right? So how many do you have now?
how many do we have now? We have, I don't remember. So we have 100. We have about 200 inverse Vanderbilt. So that's 5% of the ultimate. 5% of ultimate total for inverse
So
angle.
above 90, you can easily do, but your flow kind of shows you need maybe 100, 110.
Yeah, so this is based on PCL. Yeah, the data may or may not be the same. Data may have more.
More or less.
Since we are looking at individual jets, it doesn't matter what you are colliding actually. So you can collide E plus and minus for this individual jet. You can if there's future E plus and minus collider, we can do the same. We can also have the lepton hadron collider. For example, EIC, the problem, the energy is low at EIC. We need a very high multiplicity, high energy, high multiplicity jets. So we really need high energy. So actually, with my colleagues, we propose the idea that, so what we should do after EIC, there are a lot of discussion of the future collider in the HEP community. And one option is to build a muon collider. There's a serious discussion in the high energy experiment community. So our proposal is we will replace the electron beam by muon beam, maybe 20, 30 years from now, when the technology is ready. Then we can go to TEE. We can do the physics we propose.
But FCC doesn't get enough energy, right?
FCC will, but FCC also 40, 50 years away.
I thought it's like 1 TeV, so you just have enough.
No, FCC, you mean FCC E plus and minus. Oh, E plus, no, it's in 500 GeV or even.
It's not enough for these jets.
It's not as good as hadron collider. Because the jets we are looking at now is 500 GeV per jet.
Yeah.
So you need a TeV E plus and minus.
The muon collider could do that?
The muon collider, yes, the muon collider, because it's easier to make the muon to multi-TeV.
Right.
That's why they propose muon, right? Muon, you can make a 10 TeV muon collider. Then each jet will be 5 TeV.
Luminosity will be
the luminosity will be, yeah, that's the challenge to make the muon collider. We'll actually organize a workshop at RISE on the muon ion collider this year. If you're interested, yeah, I'm happy to invite you. Yeah, to summarize, so there has been tremendous progress made in finding and understanding QCD collectivity in small systems. That was not originally expected. So key question is how small is too small? I've shown you that we've seen clear signature all the way to the proton-proton collisions. So where else we can find this collectivity? Because this collectivity may be intrinsically built into any QCD many-body system because it's non-perturbed nature, the fundamentally non-perturbed nature. So we propose we push to the ultimate small system, as I just talked about a single pattern, and we conjecture that the pattern fragmentation process, they could show QGP-like effects. If you look at the high multiplicity ones, that has not been looked at yet. So observing this effect, this signature could shed light on a number of things: the QCD vacuum, the nature of QCD vacuum, the non-perturbative dynamic of QCD, and maybe possible entanglement, quantum entanglement. With that, I don't have experimental results yet, but coming soon. Okay.
So is the takeaway message that if you have enough multiplicity and interactions, anything will have flow?
Yes, exactly. I think this is probably a better summary than what I put here. So what do you need to create the flow, right? It may not matter that what you are colliding, right? You need to create some perturbation in the vacuum to excite the vacuum from ground state to some excited state and then generate energy and expand, right? You can do that without making colliding two objects. You can do that by just maybe shoot a particle into the vacuum. As long as the multiplicity is high enough, the effect could always show up. Yeah, that's the takeaway message. Yeah.
But non-zero flow doesn't mean there's a quadroon plasma.
Then,
If you see flow,
yeah,
that means you see quadroon plasma.
of course.
Different feeling.
Yeah. So if I see flow, then that's the first step. That's like the first observation of the ridge in QT. Next, we will have to look at all the observables we look at in high-level collisions, right? The cumulants and stringency enhancement. So we have to collect all these observables and we compare them, and then we will see whether they are same everywhere or actually they are different.
I don't find it very unreasonable. I mean, it's just, I guess if you have a strongly coupled sphere, if you go to like lower skills, and at some point you split to so many gluons and then you loop back. So
that's right.
I mean, for flow, what do you need? You need like some fluctuations to make something anisotropic, and they need a lot of interactions. And the interactions are, yeah, and strongly coupled QCD, I think they're automatically there at low enough scales. So you will have like for each particle charge, you'll have subjects which 100 eV, and that doesn't apply. But then at some point you get these interactions.
Yeah.
And if you really have a lot of particle gluons, then maybe you have a particle plasma.
Yeah, that's right. That
Could be.
basically, I think the
And in all
ultimate.
this language, I didn't say vacuum once.
Maybe I shouldn't.
No, it's just, I don't find so.
So how do you predict what you should get from this effect?
Yeah, it's very hard to predict. Well, first of all, probably we need to see something to make the serious interest. Get interested to.
If there was interest, in principle, how would you predict it?
So I think we could do. We need to make some assumption of how the initial state, the geometry will look like. You have to, and then you need to define the initial moment, energy, density profile, and maybe you can use the total multiplicity produced by the jet can be a constraint that you can define some kind of energy density profile of the jets, or the number of particles constrain the entropy of the initial stage. This part you just run the standard hydrodynamics, but you boost everything to the very high high momentum system. So your particle produced will be in a very very small cone like this. And then you just run the same hydrogenization. You can predict pi-10 protons. You can compare these to the particle composition you just. Right? So those are first order. You can use a spectrum from the JS to constrain your models. And that is first order constraint you have. I think the hardest part is how do you start it? How do you start the initial stage? Because if you think that the parton start with the point, but once they enter the vacuum, they gain the virtuality, and then some kind of size should develop, should start to develop. Some kind of geometry can start to develop. Then you
It's
should.
relatively clear, right? If you start with a 1 dB particle, I think that it's the particle shower at that scale is still well understood. So you can relax and just what you're saying.
But this is only for the early branching. But later you generate a lot of soft Coulomb radiations. Right? Those are not. I don't think we can say those are well understood.
But then the early branches doesn't that already give you the size?
At
least the answer
give
would
you
be-
a shape.
Give it a shape, yeah. Your shape could be approximately elliptic to start with, maybe. Yeah, this is something maybe reasonable to start with, to see what we get. Yes.
So you have a.
Okay, go ahead.
Do you have if you observe the V2, what is the geometry that drives that V2, or this is just a momentum anisotropy you're looking?
So I would say geometry, because from what I described in the picture I described, this come from the ray scatterings. So there has to be some geometry.
Well, you mean the vacuum have a geometry that then the parton is colliding with the vacuum fluctuation?
Is a jet shower has a job.
It's a jet or it's the
But okay, if a jet shower, is that geometry or this is just momentum flow?
No, this is geometry. I think it's not precisely to say jet shower. It's before initially, when you look at this picture, let's say initially you start with a parton and you split in, there's one radiation, and it becomes two. And then these two becomes two hotspots and then expand hydrodynamically. So that you get an elliptic geometry. So let's say hydrodynamics turns on at this point. You have two hotspots evolving. So you get the geometry.
But in that case, you're going to do also correlate that with the substructure, right? I mean, if you want to see if there's that interpretation.
Substructure of what?
Well, you have a boosted hotspot, right? Which will produce a lot of particles which are coming from the same spot.
Yeah, but it's like a dilution. It's like dilution, basically.
No, but you have a hotspot, but this hotspot is different from Heian collision where their emit rapidity, they are not boosted. Here, they are actually highly boosted and probably produce a lot of partons, including the leading hadron, right? That leading parton that is from the branching.
Yeah, so leading parton go to eta infinity, close to infinity, and then you have mid rapidity particle produced. You have, if you look at my DN d eta star, this is a rapidity distribution of the particles from the parton shower. And yes, you have the ones that very high eta, and there are also ones that closer to the perpendicular direction of the distribution.
I was wondering what, assuming this is observed, what can you learn from that sort of event that you cannot learn from the heavy ion collision? Say something genuinely new if you observe this sort of,
Yeah, I think there are a lot. Let me see, how do I phrase that? I think we will learn well, basically back to this hypothesis that producing flow effect, you only need sufficient multiplicity produced out of the vacuum in some way, right? And it will be good to verify that.
But in terms of learning something about QCD, there's some information you could extract from an event like that that you would not get out of the ion collision.
So for example, the
Actually, related to that is just that I like to know what is the relative V2, for example, the between PP, lead, and also your lead or something.
So the B2 in PP, lead and lead is measured here, and the PP is 5%, and this is like 6%. They are it's ladder in ladder system.
Yeah, sure. So that the question that can you extrapolate from this to your ELAD or whatever your part, what I'm saying, the smallest V2 you can
Yeah. So
use, and that will be your baseline, right? Because if I look at this between lead and PLAD is not that, or even PP is not that much. Oh well, okay. Depends on which multiplicity.
So if it's too small, it will be difficult to measure. And I try to. So this plot shows you 5% V2 will be here, 10% will be here, and this depends on the geometry. If somehow there's a ladder eccentricity in the system we're looking at, maybe we see ladder signal. Ladder signal. This is not a prediction. This is, we have no idea how big the signal is.
I'm trying to figure out exactly what you're proposing.
Yeah.
Are you proposing new measurements or more imaginative modeling?
The new measurement. So to measure the flow in this type of jets.
Which ones?
The jets that produce. So in one jet you produce a couple of hundred charged particles. So these are very rare jets in the tail of the. This has never been studied.
Oh, very rare.
Very rare jets. So on average, each jet will produce maybe 20 particles. So I would like to look at the ones that produce a couple of hundred particles.
A lot of if you're running actually, no?
It is a lot of yeah, we've been running.
You really need a million.
Yeah, we can't count on something to produce it. We just simply have to keep generating. Keep generating.
I guess one answer is that we're pushing like hydro to the limits, right? And that's why we got smaller and smaller systems. The idea was PLAD would already not have hydro. So once you kind of have a system like this, if it behaves hydrodynamically, well, I mean the gradients must be so large, so few particles, probably not exactly kind of be at that boundary and to understand it better. So very interesting.
It's like to push the established paradigm to extreme limit to see whether it breaks down or
these are the interesting cases.
or we'll see some surprise.
But before we go to the low limits of proton, but we first need to understand the higher multiplicity of proton. Most of the hydro fail. Disrupt the data, right? Like multi-particle Q-density. It's the simplest measurements you can do in experiment, but almost no hydro disrupt the data.
As well.
Like
So-
324, 326, you never get at least 3 times.
So what he's saying is that the quantitative description by model hydrodynamics of this multi-particle V2 in PP collision is still unsuccessful.
To get the sign.
It's true.
And although we clearly see a lot of similarity across different systems. But when you actually try to use Hydra to predict what you get in PP, that doesn't seem to work for whatever reason.
PLAD a bit better.
PLAD is much better, but it's
Yeah,
not.
bigger geometry. Because if you think about PLAD and PP, the big difference is the geometry is mainly given by the lab when you run it, right? Because we show this beautiful picture that when you somehow add the proton shape and combine with the lab, you get the precise V2. But then if you think about proton, you have to be super careful to get the shape of proton.
And how they fluctuate. How proton shape fluctuates.
Can we discuss this afternoon what is the current status of CMS? Because you present this, the CMS collaboration for these efforts. And you actually hide all the latest developments in CMS for collective flow in small systems. I'm really want to know what is updated.
Yeah, so yeah, and of course I was primarily talking about this new idea. Yeah, of course, there are a lot of other developments I'm happy to discuss.
And that's a good segue to maybe take a lunch break, and then we'll reconvene at 2 p.m. There will be a short talk by Agnieszka, but then we'll have discussion after that.
A short talk.
40-minute talk.
Oh.
A little bit short.
It's only like